till now, we know how to give masses to particles in a standard model. So we know how to give masses to H bosons, W and Z. We know that when you give masses to W and Z, the photon remains massless. So we are happy with it. Then we know how to give masses to fermions. So fermions happen to have coupling with Higgs, the so-called Tau coupling. And then after electroweak symmetry breaking, that coupling, your phi gives you mass. Okay, so for your electron, for example, there is a term which looks like E bar L phi ER, the Lagrangian. After electroweak symmetry breaking, what happens is, so in fact, I should write perhaps as L bar L phi ER. So this is U L bar phi is phi plus phi 0. Then electroweak symmetry breaking happens. So what does this mean? So this means that but in this phi plus and phi 0, my phi plus is 0 because phi 1 and phi 2 are 0, my phi 4 is 0, and my phi 0, let me write it exactly, is V plus H of this. Here V is the vacuum value and H is the small potential of vacuum times here. So what does this give me? This gives me, so mu L bar terms is 0. So this gives me E L bar V here times ER. Something that I did write yesterday, but let's cite it for the sake of completeness today. E bar L H. It will be 2 terms. Now these two have a very different character. So V is a constant. V is vacuum association value. Therefore, this term now looks like a constant times EL bar times ER. Therefore, this is the mass. So everything actually has minus sign. So minus lambda E here, minus lambda E, minus lambda E, minus. So this will mean that I get ME is equal to lambda E times V. This tells me that there is vertex which involves EL, ER, so remember yesterday also I drew some vertices. Those vertices had phi in them. So the sum of the vertices I showed you very some time. So I showed you these vertices. So there was the EL, ER and phi 0 vertex. Okay. This vertex was before the electroweak symmetry breaking. Before the electroweak symmetry breaking, which is before I mean at higher scales. Energy is higher than electroweak symmetry breaking scale. This is the diagram that shows. Once electroweak symmetry breaks, you no longer have phi 0. You only have H. After the phi 0, you take out V and goes in vacuum. So after electroweak symmetry breaking, then you have, so the first term becomes a mass, and the second term gives you a vertex like this, here and here. So again to present exactly what we are trying to find out now in meter sheets at LHC is the mass of this Higgs. So when you say mass of Higgs, it is the mass of this H and not the mass of the phi. So these are distinct things. Mass of phi was this parameter called as mu.
Why is this then called the self-interaction of the Higgs field?
This is not called self-interaction.
They say the Higgs particle is the self-interaction of the Higgs field.
No, that is a very different thing. So what is meant by that is a very different question because since you asked me, let me give you an answer. So let's go to the diagram. phi dagger phi square. Now you take phi dagger phi, you write it as d plus h, b plus h plus. Then you will get. So we have this phi dagger phi, and that will give you a term which is h. This is called symmetry. That is different from this. This is interaction with an electron. It is like a normal.
So this is what we measure at LHC. This is what will be measured at LHC.
What we measure at LHC is the mass of the Higgs. So mass of the Higgs is actually not h. Remember, it's a term which is h times something. Okay, so it's either this, it's not this. Okay. Yeah, you get one more question last time. It's very simple. You have the Lagrangian. You know what is this Higgs term in Lagrangian. All you have to do is expand the Higgs term with V and H. Okay. Whichever is a term. So we know that the mass will be coefficient of H squared. Okay. So find coefficient of H squared, you get the mass of the Higgs. It's as simple as nothing really to it. Okay. Once you are convinced that the coefficient of H square will give you the mass of the term, then that's it. Go ahead, calculate this coefficient of H square. This only gives you the strength of this vertex. Nothing else. This is not a mass. Right. This was the side. Let's go. So what we try to do today is now we try to see how to give Dirac masses to neutrinos or Mayoralder masses. So let me again go back to the point I want you to. So this is the so-called Dirac mass. Whenever you have got a term that looks like this, where you have left-handed field, right-handed field, and phi. That's the Dirac mass. Okay. Of course, we know that this kind of term will not be able to give me mass to my neutrino. That's not possible. Just like this term, phi term can only give mass to tau time, not to up time. So similarly, this cannot give mass to my neutrino. So let's see what kind of terms will I give. Yeah. So remember that to give the mass to the uptime quark, I needed a phi conjugate because I wanted to match them. So similarly, if I want to introduce this new R, the only term I should write should be of this form. So minus lambda nu, L bar, phi conjugate and nu. Okay, this would. I know it would work because it works for the U quark. So I can write, for example, so a term which is L bar, so minus lambda nu, L bar, phi conjugate. This obeys all symmetries, so SU2 and U1. Okay. Then this would be minus lambda nu, bar, phi conjugate was V 0. Okay. Let's. I'm not writing the H terms again. They're not relevant at this point. And then I have a mu r plus condition control. So now this will give me minus lambda nu times p minus u n bar. So okay. So no, as long as I do this, my electroweak symmetry breaking has given me the mass formula.
How do you determine the electroweak breaking scale?
Okay, so good question. So let's go back to the so look at these things in the grey box. What does the grey box give? The grey box gives you that the mass of W boson is half Gb. Mass of Z boson is this.
Okay, so
and
look at the scale.
mixing angle is G prime by G. So if you want to calculate V, for example, so your measurements therefore are MW, MZ and sine square error. There are three measurements. With these three measurements, you find out the values of G, G prime and V. So G, G prime and V are your so-called fundamental parameters. The measurable quantities are MW, MZ, sin theta. Okay, so for all these three, you can have different reactions whose cross sections you measure and you see where you get a peak of MZ. Then you determine T. And again, this wave of V is something that one should know exactly. Accuracy very high. What is wave of V? Wave is vacuum expectation. I will give all call it as wave. VEV, which is vacuum expectation value. Long expectation. Okay. And when you do the fit to this MW, MZ, sin theta, you get this thing to be 246. So this should always be the back of your mind. V is 246. Then now we write everything in terms of 246. So in fact, now that we know that the coupling constant of H with electron, what is this? This is lambda. Since you know mass of electron, you measure it, half an MeV. We know what is V, 246 GeV. So we know what is lambda. Therefore, we already know what is the coupling constant of EL, ER and Higgs. So when we add some future collider, if we have a, let's say, E plus E minus collision and try to find out, so E and ER collision, make a Higgs, we will know what this coupling constant is. So, coupling constants with Higgs, H and masses of particles are related. So you see, if the coupling constant of ME is lambda EP, mass of muon is going to be lambda mu times. This means that I have a vertex here which is mu L, mu R and H. What is the coupling constant here? Lambda mu. So if this coupling constant is 1, how much is this coupling constant?
210.
So I give you this coupling constant. I'm talking about 1. So what is the coupling constant? How much is it? Lambda is equal to
210.
210. So therefore, now we know all the coupling constant of H with particles because we know the masses of all the particles. That relation is not there. So electroweak symmetry making mechanism, although it was in some sense straightforward, you take something, give it vacuum and it gives you your masses. It also predicts lots of things. So in some sense, it's a very testable theory.
This was tested that the cross section is directly proportional to the mass.
You haven't seen things. How can you test?
No, like mu L, mu R cross.
You can't test it. You have to be able to make a Higgs first, no? Then you test it.
To detect the Higgs factor.
So in fact, yeah. So people are thinking of some place like ILC where you can be able to test some of these predictions. Anyway, I'm not really able to include it. Thing to remember is that V is 246. This also gives us some idea of what the coupling, Neutrino coupling constants are. Okay, so we know that lambda E times V is how much? So what is lambda E?
1 by 500.
1 by 500.
200.
1000. Yeah. So 1 by 100. Something like this. So this is 0.2 times 10 to the minus 6. Small quantity. Lambda is small. On the other hand, look at lambda of top quad. So if I want to get lambda of T. What is the mass of top quad? There are some numbers that you should never forget. About 175 G. Okay. Let me correct one here. So it's not lambda A times B, but lambda A times B by root 3. B had root 2 then, right? So this is slightly away. Root 2 times, not 0.2 but 0.2. So lambda T is 175 GeV times root 2 divided by 246. Which actually is of the order of very close to 1. So lambda T is almost 1, whereas lambda E is 10 power minus 6. So Yukawa couplings have a very wide range, 10 power minus 6 to 1, 6 or 7. We have no idea of why this range is. Okay, so given this, now you can tell me what is lambda do. So let's say mass of a neutrino is, we know it is less than 1 electron. So let's take 1 electron. So if mass of a neutrino is 1 electron volt, what will be lambda mu? Here. So it's 1 electron volt times divided by 246 G. So just give me a power.
Yes.
So lambda is 10 power minus 11. Usually whenever we have very very small quantities, one gets trouble saying why is this quantity very small. Okay. Some say the aesthetic reason. You don't want things to be as low as performance. It's okay. There is no law which prevents you from lambda performance level, but no, somehow it doesn't look good. All the coupling constants are, the gauge coupling constants are of the order of 1, 10 power minus 2 is okay. So except for something like this lambda electron, which was already very small, 10 power minus 6, there are no coupling constants which are as smaller. And now you get a coupling constant which is even about 1,000,000 times smaller than coupling constant, we call coupling for electron. So, not terribly bad, but it's a bit discussing. So, this is the reason why people are a bit uncomfortable with just giving neutrinos mass by direct. So it's okay, it's not bad. There may be some nicer way. Don't need just very small. So before we go there, let's look at the following. So let's look at UR. So we found this new particle called UR, which you want to introduce to you to know this nice derivatives. The question is, how does it act? How does it change under SU2 and U2? Now should we change to SU2? It should be singlet because all antiparticles are singlets. So SU2 should be a singlet. That is this one. Okay. What should be the value of Y? 1. So its charge is 0. So charge is 0, T3 is 0, therefore Y is 0. So this particle UR is a singlet under SU2 and has 0 aperture. What does this mean? This means that when I apply U1Y transformation, UR doesn't change at all. All the particles will change their phase, but UR will not change the phase, which is not affected. Similarly, when I apply SU2L transformation, this UR will not change. It's a singlet. No random particle changes this. So this is what is called as a singlet of standard model. So it's singlet and an SU2 plus 2. So it's in some sense an isolated particle that does nothing under the gauge loops. So this is a new one. So what we have done is we have built a singlet. So in some sense that is also not a very aesthetically nice thing, because see, standard model is built upon this gauge principle. No, that we have these gauge symmetries, everything fits in, obeys nice rules, okay, and then it's a part of our work. Then you have this new particle, which does nothing under the gauge loops, not affected by gauge loops. So what the particle doing in the standard model? It's like someone comes and refuses to obey any laws. So, singlet also means that it doesn't interact with W, doesn't interact with Z, doesn't interact with photon. Okay. Singlet under U1 means no interactions with D. Singlet under SU2L means no interactions with W1, W2, W3. Okay. So W3 and D give you A and Z. But anyway, it has no interactions with any of them. So UR will have no interactions with W, Zs and photons. So the particle that is just there, and it doesn't couple with any gauge particles. Only thing it does is couple to neutrino and Higgs to this way. That's the only term that it is. So in that sense, it's no sort of an outsider, alien particles. See, what we are doing now is we are trying to find ways of giving neutrinos a mass.
Apart from this, we see one experiment.
So we don't know if UR exists. Okay, so therefore, this is, I'm not giving this as a definitive mechanism. It's just one of the simplest mechanisms that you think of first. Doesn't mean that this is the right mechanism. We are not sure what is the right.
If you has mass, then UR should exist.
No. Because I tell you other ways by which you can get a mass. This is just one of the mechanisms. See, for electrons, up walk, down walk, there is no other mechanism which can give you mass. Okay? Neutrinos, as we will see, is the possibility of another mechanism which can give you mass.
Okay, I'll ask from a different point of view. Like, mu for electron, let's say, En is 1 minus gamma phi by 2 into whatever. I go to a frame, I change my frame, I can always give it, always measure it to be the opposite right hand.
So this is your characteristic between helicity and chirality. My En is a left chiral object. It doesn't mean that its helicity is always equal to minus 1. So there are two different objects. So I should clarify it at some point of time. So there is a concept called as helicity. There is a concept called as chirality. Okay. And people often confuse between these two. So helicity is skill in the direction of motion. Okay, in the direction of movement. So it is like sigma dot. All the arguments that you often hear, like you have a particle going and then you go faster than the particle and it becomes left, right hand. So I can do that. So I have an electron which is left hand. Okay, it's moving, it has helicity equal to minus half. So it's moving in this direction, which is left hand. Okay. Then I travel faster than the electron and look at the same electron. And then I see that its momentum has changed sign, but its spin stays the same. So something has reversed. That is helicity. So this is reversing of helicity because sigma dot p has reversed. That is helicity. Helicity operator is sigma dot p. There is something called as chirality. Chirality operator is gamma phi. So we precise for helicity operator is sigma dot p hat sigma dot. So it operates on a Dirac spinner. Dirac spinner has 4 components. So sigma is 2 by 2 object. So this is a 4 by 4 matrix. This is often sometimes called as sigma dot. So this is helicity operator. Chirality operator is this, gamma phi. When we say EL, ER, UL, UR, we are talking about chirality. So chirality operator, it means left chiral operator is so chirality is left. So chirality is left means that gamma phi acting on this side is minus. Okay, I may be wrong with the convention. So when I say that my operator, let's say I have EL. Okay, what does this mean? So I can get a convention right. So I say EL is left chiral. This means that if I act on EL by gamma phi, I will get minus. Okay, let me see if my signs are. But you know what is EL? What is EL? EL is 1 minus gamma phi by 2 times E. By definition, that is EL. So let's see what this is. So this is gamma phi minus gamma phi squared is 1 minus 1 by 2 times E. That's right. So when I talk about EL or ER or UL, UR, UL, UR, DL, DR in the contrast standard model, I always talk only about chirality, okay, not about helicity. So in the context of the question you asked, if I have a neutrino, it's traveling in some direction with the momentum P, and it has spin sigma dot P negative, left hand. I can of course go faster than that, and I will see that its spin has reversed. I will be seeing a neutrino with a right helicity. When I say I don't see UR in nature, it means I don't see a neutrino with right chirality. Okay, so very distinct. They happen to be the same in the relativistic. Extremely relativistic case, chirality is the same as helicity. So you can go to Kaljar Martin had some one of the
exactly. So that's it. So if the limit that you can neglect the masses, then they are the same.
Yeah. If you neglect the masses, then you cannot give the argument of moving faster than this body. Okay, so that's what the argument is.
Sort of limit argument.
Yeah, so this limit argument doesn't work because your assumption fails. Assumption was that a particle has mass, then you can't use it in the what you call as extremely relativistic case. But it means that the particle will be very, very fast. So therefore, we have definitely have neutrinos with left helicity. In principle, we have neutrinos with right helicity also. You have to have knowledge as mass. However, as far as we know, we only have neutrinos with left chirality. Neutrinos with right chirality, which I call as UR, have not been seen. Okay. Distinction should be
helicity is sigma dot p, projection of spin in the direction of motion. Is there a similar physical way to understand that?
chirality is helicity in the ultra relativistic approximation. say. So for this I would actually refer to Hazel and Martin. Okay. In a particular representation, called as wide representation, if you write down your Dirac fermion, it separates nicely into a left-handed part and right-handed part. Okay. And you can actually talk about it as left. So at low energies, you can talk about it as left helicity and right helicity. And at high energies, it becomes gamma phi is equal to plus 1. So this part is certain, and although I tell you in 10 lines in class, it's good if you go and read a book and be clear about it. Okay, so then we saw that this U1 is similar to SU2 and U1, so therefore does nothing. So this is the question. Why do we care so much about everything else? Why not just say that I add this U1 to standard model and that's it, everything is done. So two reasons. One is that you got something that are very small. So this, as I said, is the aesthetic reason. Second reason, which we will come to now, is that standard model doesn't allow you to do anything. You are restricted. Mostly everything should be invariant under SU2 and U1. And second condition is that anything which is invariant under SU2 and U1 should be determinate. So you have to have all terms which are compulsory, and any term that is possible to have, you have to have. So you have to give reasons for omitting a term. You cannot say, no, I don't like this term, so I won't put that term. If it's possible, you have to put it. So what happens is that with UR, you can actually get more mass terms and not just this simple Dirac mass term. Okay, that creates problems. So now let's see what kind of mass term. So before that, okay, let me remind you about antiparticles. This is going to be very so again, this is something you perhaps have seen before. So you have Dirac equation, which is gamma mu, then this I del mu minus G A mu minus N psi is equal to 0. Dirac equation in the presence of some H. Okay, so if you replace G by E, you will remove electromagnetic. That's what it is. Now, what is an antiparticle? An antiparticle should be something which satisfies the same equation, but G replaced by minus G. Antiparticle means that all the charges should be opposite. Okay. So here I give you an example of just one charge, which I call it G, but no, you can have it for any gauge root, whatever it is. So antiparticle would mean that it should satisfy this equation. With just G replaced by minus G replaced by plus G. So we agree with this. Definitely. So now I know what is psi. The question is, can I say something about psi conjugate? Psi C is the charge conjugate particle. So what can I say about this part? So let's try to relate psi C and psi. Let's see if we have something. One guess that I made is that this psi C should be something like psi star, complex conjugate. Okay, because usually complex conjugate, charge conjugate, at least words look very similar. Okay, so I take my Dirac equation and it is complex conjugate. So what happens? This gamma mu becomes gamma mu star. Okay. This I becomes minus I. Everything else stays the same. So gamma mu star minus I del mu minus G A mu minus M psi is equal to 0. This is a true equation. Okay. So that's fine. What I managed to do here is that see this relative sign between del mu and between the derivative of this term was minus. I managed to make them on the same side. Okay, because I need them on the same side for my charge conjugate. Next, I use a trick. It's a trick because someone found this trick out and it actually works. I'll tell you what a trick is. I try to find an operator which I call as C times gamma 0. Again, this is convention. What do? Let me multiply this equation by C times gamma 0. let me write it. So I had this equation which is gamma mu star minus I del mu minus G mu minus M and psi star is equal to 0. I multiply that by this quantity which I called as C times gamma. Okay. Now I choose my C times gamma 0 such that C times gamma 0 times gamma mu star times a minus sign is equal to gamma mu times C times gamma 0. So I choose my C times gamma 0 carefully such that it is satisfied. Okay. So I made an assumption that such a thing exists. But what happens if it exists? If it exists, let's see what happens to this equation. Then I get C gamma 0 times gamma mu star, okay, with the minus sign. So I get gamma mu times C gamma 0. And I have all these minus signs are taken up. So I get I times del mu plus G times del mu. Let's see. Minus mu. Times psi star is equal to 0. Sorry. Okay. Now let me see what happens. Then I will tell you if I have it like this. Okay. So now gamma 0, therefore gamma is inside, so I can just pass this. So then I can have gamma mu times I del mu plus G mu. Yeah, so this I should not have written down this M here. Anyway, let's see. So what I managed to do is write down an equation. Sorry. C gamma 0. So I figure out what I didn't figure out what to do, but it's not there. Now what do? I call this as my psi conjugate. Because I wanted, so forget about this sign of it. Okay, so it's right now let me give argument without the. I don't know whether I have any. This gives me an equation which is gamma mu times I del mu plus G mu times something is equal to 0. But this equation is exactly the same as gamma mu times I del mu plus G mu and psi C is equal to 0. Which is what we wanted. We wanted these equations. Okay. Neglect this name for them. Okay. So this means that I have been able to write an equation which is gamma mu times I times del mu plus G times mu C gamma 0 gamma star is equal to 0. So if you compare this equation and this equation, you will see that my charge conjugate of psi looks like C times gamma 0 times psi star, and gamma 0 times psi star I can write as psi bar transpose. So gamma 0 psi star is psi bar transpose is psi dagger gamma 0 transpose, which is equal to gamma 0 transpose is gamma 0 star for its emission matrix. Gamma 0 star and so psi bar transpose is gamma 0 star psi star. Let me just write down.
You should write dagger.
Oh, sorry.
Side dagger means you already taken transpose.
This is psi bar transpose. Then I write this thing as psi dagger gamma 0 and its transpose. That's there. Gamma 0 transpose is gamma 0 star. So this must be only exact representation. I think I used some representation here, which is perhaps I shouldn't have done. Okay. But anyway, so actually this part is true without any representation. I use psi c is c gamma 0 and psi star. That is my charge field. So given the particle, given the fermion, this is how I calculated charge field. So you take its complex conjugate, you multiply by c times gamma 0. So right now I assume that c times gamma 0 exists. There are arguments, there are proofs that give you c times gamma 0. So for example, if you write gamma matrices in the direct representation, you have some c times gamma 0 exists. So this Lepton just take it as given that solution actually exists. So again, let me just get rid of this n for the moment. So let's try to address a question as to whether a particle can be its own antiparticle or not. So let's take the direct equation for the particle, which is gamma mu I del mu minus g times a mu psi is equal to 0. If it's an antiparticle, it satisfies a different equation. This is g. So clearly, the same particle cannot satisfy this equation and this equation. Unless g is 0. So if you want particle equal to antiparticle for some reason, the g has to be equal to 0. For all gauge groups, I have only written down one gauge group here. Okay, but it should be true for all gauge groups. So that's one condition there. Secondly, it's possible that there are some discrete symmetries. So which means, let's say, symmetry like discrete symmetry like parity. Okay. So if particle has a parity equal to +1 and antiparticle has parity equal to -1. Of course, you can't have a particle which has the same particle with positive and negative. So as long as the particle has a charge under some discrete symmetry, it can't be heterogeneous antiparticle. So the particle must be therefore its parity. It should not have parity. Okay, if we want to write somewhere. Okay. So as long as the symmetry is conserved, you cannot have this particle. If the symmetry is broken, then yes. Okay. If someone tests the parity symmetry is broken, then it is possible to have a particle with both Newton and Now in this context, I brought this into play because nu r is a very special case. As we saw earlier, nu r was a singlet under SU2L, singlet under U11. So therefore, it is of this kind where G is equal to 0 in all the cases. For U1Y is G is 0, for SU2N is G is 0. Therefore, as far as asymmetry is concerned, nothing stops nu R from being its own antiparticle. It's possible. Okay, so this is a singlet, which means it's coupling with everything in 0. So now look at these two equations. What happens here? The top equation is del mu minus G A mu, but the G is 0 for all the cases. So it just satisfies gamma mu times I del mu psi is equal to 0. But nu R bar, the antiparticle, complex conjugate, will also satisfy this condition because G is 0. So therefore, this first condition allows, it doesn't prevent nu R from being its own antiparticle. It's a singlet. It's a singlet, therefore all these gauge conditions don't affect. So in principle I can say that it's maybe its own antiparticle. So this was the first condition. Now we come to the second condition. Second condition is about this discrete symmetry. And then we have always heard of this thing called Lepton number. So if neutrino has Lepton number 1, then an anti-neutrino should have a Lepton number equal to -1. So therefore, by our earlier arguments, just like parity, it says that if Lepton number is conserved, then you cannot have a particle which has Lepton number equal to +1 as well as -1. So if Lepton number is conserved, then it's very clear that even UR cannot be so many. So if this is actually a symmetry of standard model, and Lepton number is conserved, we are done. Then we know that most likely neutrinos get their masses because of this addition of UR. UR only has the interaction, which is Yukawa interaction, and therefore that's it. So we can all be satisfied that we know how neutrinos get their mass. So,
but it still gives the whole mass terms.
where?
It is giving whole mass terms.
Only Lepton number is binary. I told you I'll come to what mass terms these are, and you will see that both mass terms end up violating them. So if Lepton number is violated, clearly just by these two conditions. Second condition, sorry, Lepton number is conserved. The second condition here means that the particles mu r cannot be equal to its antiparticle. So let's go and talk about Lepton number conjugates. Till now, in whatever reactions we have seen, Lepton number has been conserved. I'm talking about total Lepton number. What about P and mu separate? Of course, when neutrons oscillate, you violate Lepton number L, E, L, mu. But we have never seen L mu plus L, E plus L mu being violated. That's all this is. Okay, we haven't seen it. Secondly, we can never write down any Feynman diagram, standard model, which violates Lepton number. Everything we draw has conservation of Lepton. So in fact, we know we cannot write down such a diagram. However, when I told you what a standard model was, I didn't tell you about Lepton number. Today is the first time we mentioned Lepton. I say standard model, its electroweak part is SU2 and U1. We said we build the model based on this gauge principle. Gauge principle says everything that you have should be invariant as an SU2 and U1. That's it. Okay? Nothing else. So this Lepton number is something external. No? Someone has imposed this thing on you. And this has happened simply because I have my particles up, down, electron, neutrino. If I had some other particle, maybe it's possible the Lepton number will vary. It just turns out that because I have this particular particle content, that I don't validate lepton. So no principle has forbidden this. And as I mentioned sometime back, guiding principle of gauge theory is that whatever is allowed should be there. Then we try to put some limit on the strength of this coupling factor. If it is allowed, then you put it. So by this principle, if Lepton number is not conserved, then it must be validated. If there is no gauge principle that gives me the Lepton number should be conserved, then it should be validated. So it's an artificial thing not to have Lepton number validation. This is a so-called gauge philosophy. All the conditions on your model should come from gauge principle and not from this arbitrary thing like Lepton conservation, area of conservation, parity conservation. Nothing of that. The gauge principle does not give you that, then these are something extra. Actually, you don't want extra input. So this is the philosophy. Philosophy finally tells you that Lepton number can be validated, so it has to be validated. Then you find out reasons as to why you don't see it, right? There will be some other reasons. Okay, but in principle that should be there. We are going to keep on hearing about this very, very often. And then, so just for later, I tell you that all the arguments that use this Lepton number conservation blah, 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 are all wrong. Okay. Because standard model does not conserve Lepton number. We know it doesn't conserve Lepton. Every time we study standard model, we always study that at perturbative level. No? We look at Feynman diagrams. What is the perturbative? And as you said, we cannot draw Feynman diagram which violates Lepton. Okay. However, what is standard model? Standard model is this big Lagrangian that we wrote down. Okay. Lagrangian gives rise to equations of motion. And all solutions of these equations of motion are parts of standard model. So we agree with this. Okay. All the solutions that we saw till now, okay, what are the solutions of standard of equations of motion? Solutions where electron, muon, tau, all our particles are solutions of equations of motion, the standard model. Electron, muon, tau, all of that, tau quarks, WZ bosons, and phi. They are basically solutions of equations of motion. There exists one more solution of equations of motion of this model, which is normally not talked about. Usually learn it in particle physics. I will not even teach you in this course. I will just tell you what the solution does. So let's see it. So perturbatively, let's make it very clear. When there is no Feynman diagram that violates Lepton number, this we agree. It turns out that there exists a solution of this Lagrangian. See, we wrote down Lagrangian. Okay. Once you write down the Lagrangian, whatever the solutions come out, you have to accept. They are not in our hands. Solutions exist, it has to be. Turns out that there is a solution called as a spheneron. This is a solution that allows a process which is 3 baryons going into 3 anti-electrons. Okay. Solution is reasonably complicated to write down. Okay. Enough that I won't just bring it up here. I just tell you that it exists. Okay. I can give you references where you can find it, but just take it from that the solution exists. It's non-perturbative solution. It's not a particle that you can write down as a Feynman diagram, propagator, blah. Just a combination of fields.
Then the form equation. The form equation. These 3 baryons going to 3.
So you can write down the equation of motion, but it is rather complicated. You see that it actually was baryons and leptons. Okay, so it's not simple.
What are those 3 baryons? Those 3 baryons.
Any 3 baryons, any 3 antiparticles. The solution that is not a linear thing, it's not just like a psi. Okay, it's something which involves psi 1, psi 2, psi 3, psi 4, psi 5, psi 6. And therefore, so see 3 baryons means 9 quarks. So it's a solution that involves 9 quarks and 3 anti-electrons. So it's a very messy solution. Okay, that's the reason I don't write it down. But this is a point to be remembered and won't really come into play when we are doing simple neutrino things that we want to do. So therefore I don't know. However, this exists. This is a solution which is a valid solution. This is the only non-compatibility solution. This is also solution. So what this means is that even this non-compatibility solution ends up conserving what's called as B minus L. Baryon number minus lepton number. So if 3 baryons go to 3 anti-electrons, then B, let me see if I get it correct. So I will check. Okay. But this means that you can violate B plus L, but you cannot violate B minus L. Okay. So this is something that usually people sleep under the dark, but you should know that whenever people give argument that involves L lepton number violation, they actually mean B minus L violation. Okay, so baryon number minus lepton. Fortunately, it turns out that all arguments that involve lepton numbers, you can replace L by B minus L, arguments still happen. Even when I will talk about it many times in this course, I will use the short form lepton number for B minus L because B minus L is complicated to say. So therefore, this is to be borne at the back of your mind that although we talk about lepton number conservation, lepton number violation, actually we are talking about B minus L violation, not just L violation. Because lepton number violation is not a big deal in general model, it exists. It exists non-perturbatively, but it exists.
And it comes from that solution, scalable solution, that B minus L conservation.
This is a solution that can exist. So then I'll come to this. So this was an aside. This was aside. This was a side comment away from. See, we were talking about getting masses to neutrinos, right? Not talking about B minus L. So now I'll come to the statement that I made earlier. Okay, I said that if I have new R, then I can write more mass terms. So what are these mass terms that I can write? So I can write a mass term that looks like this. Minus MR, which is the coefficient, new R conjugate R, new R. So I just give you this term. Let us examine this term with all our symmetries that we have. What are the symmetries that we have? SU2, U1. That's the thing to be checked for the first. What about SU2M? Is it easy to see that there is no problem? It's a singlet. It's a singlet. Everything is a singlet. Both are isospin 0. Add the two, you get isospin 0. Fair. SU2 is fair. U1. Zero. So I can write down this. I don't need to use Higgs. I don't need anything. I can just write down this term. So there is a nu RC, which is my charge conjugate particle of nu R. So I had a nu R. I told you how to get charge conjugate of nu R. Take C gamma 0 times nu R star. So this I can write down a particle called nu RC. Okay. I can, so term should be of the form psi bar psi. So I said nu RC bar times nu. So this I can write. This is the Lorentz scale.
Term should be of the form psi bar psi. What of the value for mu doesn't have any G is 0. SU2 square.
can be of the kind of UR from the previous argument. So yeah, so we actually come to that. But yeah, so I wrote this down because this is the standard form. So UR, if UR conjugate, and then okay, so I tell you why UR is not because I'm being slightly strict here. UR is a Dirac spinner. So what is Dirac spinner? It's a 4 column vector. So you can't circulate UR. You have to have some sign, bar sign, because you want a Lorentz scalar. Then you can write a row vector and a column vector. So psi bar is row vector, psi is column vector. You multiply them, you get a number. That's Lorentz scalar. So you can't just write UR. So this term obeys SU2, obeys UR. It violates B minus L by 2. Because B minus L. So forget about B, there are no variables here. So just talk about Lepton number. In Lepton number for mu R is 1, which is Neutrino. Lepton number for mu R conjugate minus 1. So Lepton number for mu R conjugate bar is plus 1. So this term has Lepton number is equal to plus 2. Or you can say B minus L number is minus 2. Whichever way. Okay, so Lepton number. So it's rather Lepton number by 2. So if Lepton number was conserved, you could say this term is not allowed. But now we are allowing Lepton number values. Because we are allowing that, this term is allowed. So we can have this. This term is what is called as Mayer allowance. So if Lepton number vibration is allowed, then we can write a term like this in the Lagrangian, and this term is called as Mayer allowance. So we are saying we are allowing it to be. So this is a symmetry that standard model does not impose on it. It is just observed. So this term is often written like this. So this MR minus MR UR C bar UR. Very often you write URC. Okay. Just a matter of caution. When I say URC, it actually means okay, it is not equal to. Okay, there is often some confusion about this. It's possible to write down something like this, but then you have to then write brackets around it. Without bracket, convention is μRC is the charge conjugate of μR. Okay. μRC is a left-handed object. μR is right-handed. It is charge which is CP conjugate. It's actually a left-handed object. Okay. So this is true. Okay. This is not. This is convention. So I take my μR first. See. The way I look at it, I never talk about mu and then take its left-handed term. I talk about UL and UR as my different options. There is nothing like mu only. Mu R and UL. So mu C is no meaning. We should come at the bottom of this transparency. See, if any time I write a term, it always comes with plus Hermitian conjugate. So Hermitian conjugate will take part of your engineering. me write this down. So mu r c r times. Okay. One can show that mu r c times r times mu r is actually the same as mu r bar using algebra of this charge conjugation. Psi c sin using this mu r c is equal to c and what's equal to mu r star. One can show that mu r c bar mu r the same as mu r bar. So therefore, when you write this term, you often write this term as minus half mr mu r c bar mu r minus half mr mu r bar. So this just for the convenience of writing, because then you can write this thing simply as minus half mr mu r c bar mu r plus its summation, because this is summation conjugate, but it's also identical to it. So you can always write it like this. Okay. So therefore, this term, which is minus mr times mu r c mu r, is often written as minus half mr times mu r c bar mu r plus mu r bar mu r c, which is minus half of this plus summation. So you will often see it written in this way. Okay, but all these 1, 2 and 3 are the same forms. So before we leave today, I'll give you this last one. What is, we talked a lot about particle, antiparticle, right? When they can be seen. Now, I define something called as nu. I say my nu is mu r plus mu r conjugate. Okay. And then you can see that if I take antiparticle of nu, it is just nu. Okay. So therefore, now I can say that my nu is its own antiparticle. Nu r is not its own antiparticle. If I take nu r charge conjugate, I get a left-handed object. So that can't be antiparticle, that can't be the same as mu. It's only the mu r plus mu r c is the antiparticle of mu. Is mu, and then this mu is the okay. Why can I do this? Why can I not do this for electron? Why can't I say that EL and EL conjugate?
Charge conjugation is not equal to that.
It's for charge conjugation. So what? See, EL satisfies one equation. Okay. EL conjugate satisfies something else because it's a positron. Okay. Therefore, EL satisfies Dirac equation. EL conjugate satisfies Dirac equation. But EL plus EL conjugate will satisfy another equation. Because one of them satisfies with plus E times mu, second satisfies with minus E times. So here I can add them because mu r and mu r conjugate satisfy the same equation. Okay, because there is no charge. That is the reason I can do it for mu r. I cannot do it for any other particle. Because mu r is a singlet under SU2 and u1, is why I can write down this mu and make mu r and mu plus mu r equal to 1. Okay, because if I have an equation, linear equation, I have two solutions. I can say no, psi 1 plus psi 2 is also a solution. This is what I am doing here. I have a Dirac equation without any complete constants. Mu r is the solution, mu r c is the solution. Therefore, mu r plus mu r c is the solution. So then I can call mu as a particle. Okay. If I had taken EL and EL conjugate, EL plus EL conjugate is not a particle. It doesn't satisfy Dirac equation. So that is very important. So only in the case of mu r, which is a singlet under SU2 and u1, is when I can say that mu is a particle, which is mu r plus mu r c. and this is a Majorana part because it is no antibody.
This argument is not valid for new L. Because it has the
It has y, right? It also has y. So mu L has a y. So I cannot say that mu L plus mu L C is its own identity. Not at this point. Okay, because I want to satisfy this U2 plus 2. Okay. And then you can see that in these terms, I can write down my Lagrangian, which is this part, as minus half mr times mu bar nu. See, mu bar nu minus half then this mu bar nu is so mu is equal to mu bar is mu r bar plus mu r c bar. This is mu r plus mu r c. Okay. So if I combine them, I am going to get mu r bar mu r plus mu r c bar mu r plus mu r bar mu r c plus mu r c bar. So can you tell me why some of these terms vanish? So you should be able to use left-handed, right-handed, handedness arguments to see which one is Spanish. Yeah, so what happens to the first term? First term will vanish because mu r is right-handed.
We'll take projection of a
Mu r
right
bar
hand
is
on the
left-handed.
projection on a right hand is on the left hand.
So it's vanishes. This vanishes. This is right-handed. URC is left-handed, but bar is again right-handed. So this is okay. This is okay. Okay. And this again will vanish. So then these are the two terms that survive. And now you see that these two terms are exactly what we had written on before. These two survive. So all these statements are equivalent. Okay, so on this transparency gives a few unrelated statements. Okay. One is that the Majorana mass term is mu bar nu. Second is mu it is so antiparticle. Third is that Majorana mass term is mu r c bar times mu r. But all these three as we see are related. So all these tend to go the same. So what we have seen today is that, of course, you can put in the mu r and say that I need to reduce the mass, but your problems don't end there. It has created more problems. Once you have mu r, you have to have this. And as we said, as long as we allow this p minus n migration, then this term has to be there, and we have to live with its consequences. So we'll see in the next class what are the consequences of getting such terms to some other mass terms to mu r. So it's not as straightforward as p in mu1 and mu2. You get into big mess.